I'm going to pick up where we left off. Quick recap. Today we're going to be talking about, it's still too loud. Paul? Yeah. How about now? Can you hear me at the back? Perfect. So, what we've seen so far is that multi-electrons can be constructed to represent pretty much any function. You give me a function gx, I can always construct an MLP, pose this function. Question is, how do we construct this function? So when I speak of how do we construct this function, the question we're really asking is, as we are going to assume that the architecture of the network is given, how do we determine and the bi neurons in the network? So now, if you want to do it in a theoretically correct way, what you would do is to define a divergence which quantifies the error between output, something's odd, yeah, the actual output of the network and you want the output to be. And then you would compute this expected divergence over the entire input space, and you would estimate your parameters of the network to minimize this expected divergence. Now the problem, of course, is that we don't actually have the effects that we want to. So what we do is to sample the function. Say we collect input-output pairs, lots of x values and the corresponding function output, number of, and if you're sampling things properly, these samples will be drawn from the natural distribution of the input data. For as far as we are concerned, this basically is collecting samples from the world. And then we'll estimate the function from just these samples. We don't have the entire function g of x. We're going to estimate the function from these samples. So is to estimate of the expected divergence between the true function and what the network is actually computing. Do you mind shutting your laptops at the back? Please shut their laptops. Thank you. So we're going to compute the empirical estimate of this expected divergence. The empirical estimate is that for each of these training points, we will compute the divergence between the output and the desired output and compute the average divergence over all of these training points. And this we will use as an approximation for expected divergence between the output of the network and the true function. Now, this is our best guess for this guy, given our training. We cannot really do better than that. So the hope over here is that by minimizing this error, we will actually be minimizing this term. There's no guarantee that this is going to happen. This is stand. And so here is the entire setup. We will be given a training set of input-output pairs, a number of input values x, and the corresponding desired output. And on each of these training instances, we will define the divergence function, which is a measure of the error between the output of that network for that input and the desired output of the network for that input. And the average of these is what we will call, I've written this as error, we also often call it a loss. The point is it's a function of the parameter. And we are going to try to estimate this to minimize. So this is an instance of, it's an empirical risk because you're basically computing the risk of the entire input space.
You can keep that one on.
Yeah.
There's some issues I got to look at later, but yeah, you leave that.
So it's the empirical risk because basically you are computing the error over drawn sample. So this is the weights, and we are trying to minimize it. So it's an optimization problem. We also quickly saw we went through a crash course on function optimization in the last class. Say you're given a scalar function of some some input. Then we saw that the point at which this function takes a minimum value is the one where the slope is 0, where the gradient or the derivative is 0. So the easy way to solve for this minimum is to simply explicitly compute the gradient and set it to 0 and solve for the point x at which this equation is satisfied. But that is not sufficient. That could give you either a minimum or a maximum or some kind of a saddle point. So you would also check the double derivative. In the case of functions of multivariate inputs, this double derivative is going to be a matrix, a Hessian. And if the location where this equation is satisfied as a minimum, the Hessian will be positive definite. If it's a maximum, it's going to be negative definite. What we mean by positive definite matrix is one where all the eigenvalues are positive. A negative definite matrix is one where all the eigenvalues are negative. And if neither of these is satisfied, then it's neither a maximum nor a minimum. The real problem is that this kind of solution is not going to be possible for most functions because you won't actually get nice closed form formulae that you can solve for and find the minimum. So we're going to use an iterative estimate. So what we will do here is to begin with some kind of a guess, and which is your current guess for where you think the minimum of the function is. And then you look around and you say, hey, no, the function is decreasing if I travel in this direction, so you take a step in that direction. You repeat this process, you're going to keep walking down the function, and eventually, hopefully, you will arrive at a location where the function no longer decreases, and that is going to be your estimate for where the function is a minimum. Now, the question is, which direction do you step in? Which direction must we travel, must this estimate be moved in to actually decrease the value of the function? And when it's moved in this direction, how large must the step be? So these questions we will answer by and by, but so overall, here is the trivial algorithm. There is an answer for which direction to step in, and that is based on the derivative. We want the gradient or the derivative is the direction in which the function increases. So if you want the function to decrease, you're going to walk against the gradient or the derivative. That leads us to this trivial iterative algorithm. You start off with some initial value x0, and while the derivative is greater than some epsilon, or there's an alternative, while the function is still decreasing, you take a step against the current gradient. Now, so here, I mentioned that the derivative of the function is 0 at a minimum. This is not always going to be the case. You can actually have minima where the derivative is not 0. We're going to see an instance of that during this lecture. So this other one is probably a better choice for when to stop iterating. So here's the overall gradient descent algorithm. You initialize your estimate, and while the function is still decreasing, you compute the gradient at the current location and keep taking steps against this gradient to find the minimum. Right? Everybody with me so far? So nothing new. One small thing that we will encounter in the next class when you're doing some sort of a gradient descent, if you have functions of this kind, nice and convex, gradient descent will eventually find the minimum. If you have uglier functions of this kind, you really have no idea which point gradient descent is going to arrive at. It could arrive at a local minimum, it could arrive at a saddle point, it could arrive at a global minimum. It all depends on where you start. We have no control over it. Anyway, let's return to our problem. So here is the problem statement. You're given a set of training instances, input-output pairs. We define an empirical estimate for the expected divergence, which is the average divergence over all of these training instances. And we want to minimize this divergence with respect to the argument w. Now, this is very simply stated, but then there are many holes. This function is not yet properly defined. We have to answer many questions. What are these input-output pairs? Where did they come from? How do you represent them? What is this function f that we claim is going to approximate the function that we're trying to learn? What is this divergence that quantifies the error between the current value of the function and the value that you want it to be? So all of these must be answered, right? Let's start with this definition of the function itself. Now, clearly, this is easy because we are working with neural networks. So that function is a neural network. It's a multi-layer perceptron. Specifically, we're going to have a directed network where the values flow directly from the input to the output, and no neuron actually sees any input more than once. The output of a processing does not come back to the neuron. It's directed. Generic terminology, where you often hear of this term, an input layer or input units. When we speak of input units, these are not neurons. These are just the input. We will not actually think of these as neurons. We will not count this as part of the network. And then you have a bunch of hidden units. Hidden units are units whose outputs you don't actually see, but whose outputs affect the final output of the network. And then you have the output units, whose outputs are the outputs that you actually see. We're going to think, for convenience, that this network is layered. So when I speak of layers, it means that the neurons can be arranged in layers, and all the neurons in one layer only communicate with the neurons in the next layer and not the layer thereafter. Right? I mean, this is just for convenience. We will, in actual practical design, we will flout this particular assumption. So this would be the input layer. These are hidden layers. That is the output layer. Now, within this, we have to define the individual units, and we've seen this unit before. Here's the standard setup. You first compute an affine combination of the inputs, which is some weighted sum of the inputs plus a bias. And then, this affine combination Z, you apply an activation function f on it, where the activation function is differentiable. Now, this is a specific format. You can actually generalize this. You can think of the entire neuron as an arbitrary differentiable function of the inputs with some parameters. But thinking of it in this manner actually makes things very complicated. We're going to sort of stay with this. This is the standard format that we will use for neural networks. Questions? No? Now, here are some typical activation functions. So we've seen this in the last class, the sigmoid. Again, the activation function is how it works on this affine combination of inputs. So the sigmoid is just 1 over 1 plus e raised to minus z. And if you compute the derivative, that's simply going to be f of z times 1 minus f of z. It's very easy to compute, so I will leave this to you as an exercise. So also, we also encountered the tan h. The tan h is basically just the sigmoid shifted down by half a point. So and the derivative of that is going to be 1 minus f squared of z. And then we have other kinds of activations. We've seen this in the last class, the ReLU, which is basically a hinge function of this kind, where the output is 0 when the input is negative, and the output is the same as the input when the input is positive. This one is obviously not differentiable at 0, but then we will define the derivative in this manner, that the derivative is 1 when the output is greater than or equal to 0, and 0 when the input is greater than or equal to 0, and 0 when the input is negative. There's also the smooth version of it, which is log of 1 plus e raised to z, and the derivative of that actually ends up looking just like the sigmoid. So various definitions of just the activation function. Now, we can also have all of these activations are assuming that there's a single input z and a single output y, which is a function of z. But then you can have these situations where you have a function which operates on a combination of inputs and produces a combination of outputs. I will call these vector activations, as opposed to these guys, which I will call scalar activations. So in a vector activation, the input is a vector, the output is a vector. Every one of these x's, what happened? Every one of these x's potentially affects every one of these y's. So here is an example. This is something that you've already encountered in your homeworks, and we will see a lot of the softmax. So I have some inputs. The vector activation function is just this portion of the diagram. So the z's are various affine combinations of these inputs. And the output y's are simply the exponentiated versions of z's, but normalized so that they all sum to 1. And then over here, you will actually see that if I change, it's very easy to say what distinguishes this from other activations is that I have yi equals e raised to zi over summation j e raised to zj. What happens if I increase z1? If I increase z1, will y1 increase or decrease? It's going to increase. What happens to the other y's? They decrease because they must all sum to 1. So here's what you will find, that if I compute the partial derivative of y with respect to yi with respect to zi, that's simply going to be e raised to zi over summation e raised to zj minus e raised to zi times e raised to zi over summation j e raised to zj squared, which is going to be y minus y squared, yi minus yi squared, which is yi times 1 minus yi. I assume all of you see actually what, where this equation has been derived from. So I can change this guy, and I can compute, if I change z2, I can actually compute how y2 changes. But then I can also, although I can also compute the derivative of yi with respect to some zj, where j is not equal to I. And that is going to be e raised to zi times minus e raised to zj over summation e raised to zk squared, right? Which is going to be yi minus yi yj. You can actually work, it's very trivial to see. So you can actually, which means that I can actually compute I can change this guy, and this output is going to change, and the derivative is given by this formula over here. If I change yj, how much zj, how much does yi change? So you can have other kinds of activations of the same kind, where maybe I multiply all of these guys with different exponents, and I'm going to get a bunch of outputs. And once again, changing any of these zi's is going to change all of the yi's, right? So these are what I call vector activations. And in fact, in a layered network, I can think of every layer as in fact being a vector activation where a bunch of inputs come in and a bunch of inputs go out. So the special case where each neuron only responds to the local zi that's just a special case of a vector activation. So it's convenient to think of things in this manner. Notation, I'm going to, there is no eraser, okay. So notation, here is the notation I will use. This notation is slightly different from the one I used in the last class. I have to go back and correct my slides. So wij is going to be the weight of the connection from the ith neuron in this layer and the jth neuron in this layer, and the superscript is the index of the output layer. So wij1 is the weight of connections from the ith unit in the 0th layer to the jth unit in the first layer. wij2 is the weight of the connection from the ith unit in the first layer to the jth unit in the second layer, and so on. The bias bj superscript is simply the bias applied to the jth unit in the second layer. So the output is going to be the output, or the network itself is simply going to be the output of the final layer. Now, so we've sort of specified this function f completely. What about these inputs? These input-output pairs. These are just the data that you're going to collect. Now, here, if I'm given a training set of input-output pairs of this kind, then this x1 itself is going to be a vector with a number of components because the inputs are all vectors. This d1 is also going to be a vector, potentially a vector, because for any given input you can have any number of outputs. And the output y also is going to be a vector. So this is the desired output, y is the actual output, which means the dimensionality of y and the dimensionality of d are going to be the same, because the actual outputs should be you should have the same number of actual outputs as the number of desired outputs. Now, this first index n refers to the specific training instance. Very often we won't actually index the training instance, but talk in terms of individual instances for convenience, because notationally adding that extra index doesn't really buy you anything but really complicates things a whole lot. Now, what are these values? The inputs are going to be vectors of numbers, or it could even be a scalar, just a single number. So for example, these could be pixel values in an image, or these could be vectors of speech features derived from a speech signal, or these could be a real valued vector representing text. We will see in a later class how you can actually derive vectors, real valued vectors to represent text, or any other real valued set of real values. The output depends, how you represent the output depends specifically on the kind of function that you're trying to compute. So if the desired output is real valued, then this output is simply going to be a neuron which produces real valued outputs. If the desired value is the desired output is a vector of real values, then these neurons are simply going to produce a vector of real values. You will have to choose the activations appropriately. Now, if you're trying to perform classification, let's say you're trying to perform binary classification. When you're performing binary classification, then the output is going to be either of one class or of another class. So I can represent binary outputs using a binary number 1, 0, in which case I'll have a simple 1, 0 representation of the desired output, where 1 represents one class and 0 represents the other choice. So for example, if I were trying to analyze images and determine whether this was an image of a cat or not, then I could say the output is 1 if the output is if the image is a cat, or the output must be 1 if the image is a cat, and 0 if it is not. Now, typically in these cases, this output neuron is not going to be a simple threshold unit which only produces ones and zeros. It's actually going to be a sigmoid. We saw this in the last class. And in this case, you can think of the sigmoid as producing the probability that the output is 1, given the corresponding input. And this, the nice thing about the sigmoid is that it's differentiable, and it also captures the fact that for any given input x, for any specific value of x, in any realistic data set, you're going to see both labels more often than not, but some labels of one class of labels is going to be more frequent than the other. So this is a much more realistic way of representing the output than a simple threshold. Now, if you have multi-class classification, consider a network that must distinguish if an input is a cat, a dog, a camel, a hat, or a flower, then you have 5 arbitrary classes in this case. So what we will do is to decide upon a specific order for these 5 outputs. So maybe cat, dog, camel, hat, flower. And that any time you want the output to be, say, a cat, the output is going to be a 5-dimensional vector where the output value is 1 in the cat position and 0 elsewhere. If you want the output to be a camel, then the output is going to be a 1 in the camel position and 0 elsewhere. So every target output is going to have as many dimensions as the number of classes, but the desired value is going to be 0 for all the non-target classes and 1 for the target class. So this is what we will call a one-hot vector, because there's only one entry which is hot, the rest are cold. Now, when you're performing multi-class classification, then if you want to perform, build a neural network that can perform multi-class classification, you will have as many outputs as the number of classes. And the desired output is going to be, is that these outputs must be 0 for all the outputs corresponding to the non-target class, and must be 1 for the output corresponding to the target class. In other words, ideally the output must also be one hot. So if I say that the first output is cat, the second output corresponds to dog, the third to camel, and the fourth to elephant, and I give you an image of a camel, you want the first, second, and fourth outputs to be 0 and the third output to be 1. So it's now more realistically, you're not actually going to get these nice clean outputs. What you will get is a bunch of positive values that sum to 1, which can be viewed as a probability vector, which actually corresponds to the probabilities of the individual classes. And most commonly, we're going to use the Softmax activation layer at the output, the one that we just saw, where you would have the penultimate layer is going to produce some outputs. The output layer itself is going to work on affine combinations of the penultimate outputs, and then you have the Softmax activation, which gives you the probabilities of the individual classes at the output. So in a typical problem statement, if you're given a number of training instances, say images of digits along with information about which digit the image represents, you could have different tasks. You could have binary recognition, which says, is this image a 2 or not? Or multi-class recognition, which digit is it? Is this a digit in the first place? So these are two different problems. So if I were trying to just perform binary classification, these training instances, the corresponding labels would be as shown in red. This is not a 2, so the output is 0. This is a 2, so the output is 1. This is a 2, so the output is 1. 4, the output is 0. So these are the desired. What's shown in red is the desired output of the network. And because this is a binary classification problem, your network only needs to have one output whose value is going to be between 0 and 1, and gives you the probability that the image that it sees is actually a 2. Now, if you're trying to perform actual digit recognition, then these are the desired outputs. When it sees this image, you really want the network to say, I saw a 5. So now the network is going to have as many outputs as the number of classes that you have, and will have a structure of this kind. Now, we've defined the function, we've defined the inputs and outputs. The last thing that we want to worry about is this divergence function. First thing, you want the divergence to be differentiable. If the divergence is not differentiable, then this error is not differentiable. If the error is not differentiable, you will not be able to find the optimal value of W. So here are different kinds of divergence functions that you can define. If you have real valued target outputs, then these outputs for any given input are all going to be real. These would be the desired output. This is what you want the network to actually produce. And the divergence is going to quantify the difference between these two guys. If both of them are identical, ideally the divergence is going to be 0. If they're not identical, you always want the divergence to be positive. So it quantifies that these two are not the same. Now, for real valued outputs, there's a very simple standard divergence measure, which is simply the squared Euclidean distance between the actual output and the target output. The reason we use the squared Euclidean distance as opposed to a magnitude is that the squared Euclidean distance is nice and quadratic, and it's differentiable. And of course, you can see that if I differentiate it, you're just going to find it's going to be half of the squared Euclidean distance. This half is just a scaling constant. For convenience sake, because when you differentiate it, you find that the derivative is simply the actual difference between the target output and the real output that you get. So this is just a vector of errors. This is in the earliest versions of neural network training, people worked with these L2 divergences. And when you have in the L2 divergence, the derivative of the L2 divergence is really just the error between the actual output and the desired output. And so the algorithm was very often called error backpropagation, in that you compute the error and move it back through the network. For binary classification, you're going to have an output which goes between 0 and 1. As we saw, this is the probability of the class 1. And then you have the target output D. And the most useful divergence function over here is the Kullback-Leibler divergence, which consists of a first scalar, which is the entropy of the output, and a second term, which is the y, which is actually a function of y. So this is the one that we are really interested in. This is the cross entropy loss between the actual output and the desired output, which is minus d log y minus of 1 minus d log of 1 minus y. It's the cross entropy between d and y. Observe that y is a probability. D2 can be thought of as a binary probability where the probability is either 0 or 1. And so this is the cross entropy between the two. And if you take the derivative of this guy with respect to y, observe that d is either going to be 0 or 1, right? It's the training input is either belongs to the class or it doesn't belong to the class. So if d is 1, the derivative is this term becomes 0, and the derivative is simply minus 1 over y. if d is 0, this term becomes 0, and 1 minus d becomes 1, and the derivative is simply 1 over 1 minus y. Now, here's something really cool. Look at this guy. Now, if the target output equals if y equals d, what is the divergence? When y equals d, consider d is 1. When d is 1, this term is 0. You're only left with d log y. But if y equals d, y equals 1. So log of y is 0. And so d log y is 0. So the divergence actually becomes 0 when d equals y. On the other hand, look at the derivative. What happens when the output is exactly what you want? Is the derivative 0? Anyone? No, right? It's minus 1 over y. So if the desired output is 1 and the actual output is 1, you get a derivative that's actually minus 1. So we've been saying all along that, now, can this divergence actually go below 0? It cannot. It's a divergence function. So although the divergence has hit its minimum, the derivative at the minimum is not 0. So you are not always going to, and why is that? Anyone want to take a guess? Why? Yes?
Because the minimum is in the edge of the domain.
The minimum is at the edge of the domain. Y is only allowed to lie between 0 and 1. So here's a function. If you let y go beyond 1, the function would keep decreasing. But you're restricting y. Anytime you pose a restriction on the domain, there is no guarantee that the divergence is going to decrease. On the other hand, that the derivative is going to go to 0. On the other hand, you are guaranteed that when you hit the correct answer, the divergence will not decrease further. Which is why when we were looking at the gradient descent algorithm, the condition that I imposed was that the divergence must not decrease any further, right? Just keep note of this. Now, when I have multi-class classification, the desired output is going to be 1 hot, where I have a 1 in the position of the class and 0 elsewhere. The actual output is going to be a probability distribution, assuming you're using a softmax. And so once again, I can define the cross entropy between the desired output and the actual output. And the cross entropy again is going to be minus summation over all of the components di log yi. But then since di is 0 for all but the target class, this simply becomes minus of the log of the output for the correct class. And once again, if I compute the derivative, you can see that this, because it's only a function of the output for the correct class, when I take the derivative of the divergence with respect to the various yi's, the divergence doesn't depend on the y values for any class other than the target class. So the derivative with respect to the non-target class outputs is 0. The derivative with respect to the target class output is minus 1 over yc. Now observe something very satisfying about this, that ideally the output is 1 for the target class. When the output is less than 1, you have 1 over some value. This is going to be it's going to be a negative value, and which means that the derivative is negative, which is really telling you that when the derivative is negative, do you want to increase the argument or decrease it to reduce the function value? You want to increase it because the derivative is pointing downwards. You're saying increase y. So you have this nice little very intuitive equation which tells you that you must somehow increase y in order to decrease the derivative. And once again, over here, note that when y is actually equal to d, the divergence, the derivative is not 0. Right? Now, just sometimes, even though you want the output to be, you want the target output is some class C, you won't actually use a one-hot representation. Instead, you'll assign a small probability C epsilon to all the non-target classes. And for the target class, you're going to assign a probability 1 minus k minus 1 times epsilon, where k is the total number of output dimensions. So this is what we will call label smoothing. where you assign a small non-zero probability to all the bogus classes. It turns out, although arithmetically speaking, this is wrong. You know the actual class of the training instance. This little trick will often give you gradients, better gradients for gradient descent than if you actually use the one-hot representation for the output. So in your homeworks, for instance, you might want to try out label smoothing to see if it helps you during training. Yes?
Why is that the case that sometimes it would be useful to smooth it out?
Simply because what happens is if the when you actually get to the target value, it turns out that if you give something of this kind, then your sigmoid can actually overshoot it. And so you actually end up getting gradients. It's a heuristic, it's a hack, but it works, right? Now, so here's the problem setup. We have defined pretty much all of these terms. We are set to go. Questions? Yeah. Over here, so you want me to explain why when the over here, that's simply because I've used this one over here, right? So if you take this log, when I'm taking a derivative with respect to yc, this is the term that I have for log y. Y is 1 minus k minus 1 epsilon. For the rest of them, it's epsilon. That's all. Oh, this should have been, sorry. Yeah. So d is going to be this guy for yc, and d is going to be epsilon for the rest of them in this particular case, right? Was that the question?
Not for this part, the part that yes, for this part where we said that when y is equals to d, the derivative is not 0.
Yeah, so when y equals d, right, then look at the derivative for the cth component. Yc is going to be 1. Minus 1 over 1 is going to be minus 1. So the derivative is not 0, right? And are you asking me why this is the case? Okay, so that's because if you actually plot this function, this is y, this is divergence. This divergence is going to go something like that if I'm right. Or maybe it's the other way. But then y is not allowed to go outside this range, right? So at the boundary, where the divergence is 0, the derivative is minus 1. Make sense? Yeah. Okay. So here again, to recap, is the gradient descent algorithm. And observe now that I've actually said you want the, as you keep taking steps, eventually you want the divergence to plateau. Right? Now, if I want to do this, let me expand this guy out. This xk in our case is going to be the set of weights, right? So if I actually write this, now the set of weights has many, many components. You have every weight for every, between every pair of neurons, between every pair of layers. So basically, when I say this, I'm writing this as in terms of a simple gradient, but what you're really saying is that for every component, you want to compute the derivative of the divergence with respect to that component, and then take a step against that derivative. So in terms of training neural networks, here's what it's going to look like. You have this error, which is the average divergence over all of your training values. And then you're going to initialize all of your weights and biases. I'm assuming that the bias is also represented as a weight for convenience. And so we're going to initialize all of them to some value. And thereafter, now here's one thing. You don't want to initialize all of your weights to be exactly the same, because now that ends up being a stable point. So you want to actually have these things be different. But then once you do that, I can go through every layer, and for every pair of input and output neurons between the layers, I'm going to have a weight wij, k, and each weight is going to be adjusted in this manner, where I take a step against the derivative of this error for that input with respect to that weight. I'm going to take a step against this derivative, right? So, and we keep doing this until the error has converged. So for every layer k, for all ij, you're going to update wij_k as wij_k minus some step size times the derivative of the error with respect to wij_k. Just straight up gradient descent. So the key point that we really are interested in is this guy, the derivative of the error with respect to wij_k. And, well, here's the total training error. It's the average training error, average divergence over all the training instances. So when I compute the derivative of the error with respect to any parameter, because of the linearity of summation, it is the average derivative of the error for the individual instances with respect to that parameter. So what we are really interested in is this guy. For any given input x, what is the derivative of the divergence between the output of the network for that input and the target output of that network with respect to the parameter? So this is what we have to figure out how to compute, right? So questions? No. Okay. Does anybody see a duster or an eraser over here? It's odd. It's a classroom without a duster. Anyway, so we saw this in the last class. How exactly do you define the derivative of a function? So if I say y equals f of x, then what is the derivative of the function? So the derivative of a function is literally defined as some term alpha. If I say y equals f of x, then the derivative is some term alpha such that for any small increment delta x, the corresponding increment in y can be written as alpha times delta x, right? So this is how we actually define the derivative. This is the only way to define the derivative. So we often write this derivative as dy over dx. And so this is what the real interpretation of a derivative is. For a small change in delta x, the corresponding change in delta y is going to be dy over dx times delta x. That is the definition of the derivative. So when I have, so for example, if I have a differentiable function of many inputs, once again, we saw that here the output is a scalar, the input is a vector. Then I can write that once again, I can use the same equation. We saw this in the last class, except this term is now going to be a vector, which means this term is also a vector. And the change in y is going to be the inner product between alpha and the corresponding change in x. And if you write it out, that's simply going to be alpha 1 times delta x1 plus alpha 2 times delta x2 and so on. We saw this in the last class, right? And those alpha terms are the so-called partial derivatives. So this, everybody's comfortable with this notion because we're going to beat on it a little bit, okay? Now let's say I have a nested function. If I have a nested function y equals f of g of x, right? Let me break this function down. I can first write z equals g of x. Using the definition of derivative, delta z is going to be the derivative of g of x with respect to x times delta x. I can write y equals f of z, which means once again using this definition, delta y is going to be the derivative of f with respect to z times delta z. But then delta z we see from this equation is the derivative of g with respect to x times delta x. So if I write delta y in terms of delta x, this guy here is the multiplicative term. The derivative of f with respect to z times the derivative of g with respect to x. So therefore, the derivative of y with respect to x is the derivative of y of f with respect to g times the derivative of g with respect to x. So it's a simple chain rule, but I've shown you how the basic definition of the derivative gives you this rule, right? Now, I can have a distributed function. I can have y be a function of many g's, each of which is in turn a function of x, right? So then when I want to compute the derivative of y with respect to x, that's going to be the partial derivative of f with respect to g1 times the derivative of g1 with respect to x plus the partial derivative of f with respect to, this should have been g2. Okay, some of you guys at the back, can you know that there's an error over here? Okay, so there's a partial derivative of f with respect to g2 times the derivative of g2 with respect to x, and so on. And if you actually start off with this basic definition of the derivative, I won't actually go through this. It looks a bit tedious. It's not. It's a two-step thing. You can sort of verify for yourself that you can actually start off with this definition, and it will give you this equation for this distributed chain rule. But then there's actually a much nicer way of looking at the whole thing. And the nicer way of looking at the whole thing is what I will call an influence diagram. This is something that you might find it worthwhile getting used to, because this is a really convenient way of figuring out what derivatives are going to be like. So here, for example, consider y, which is a function of g1, g2, all the way through gm. Again, this should have been g2, right? And each of these functions is, in turn, a function of x. So in that case, x modifies all of these g's. All of these g's modify y. So anytime you modify x is going to change g, and that is going to change y, and the net result over here is going to be additive. So dy over dx is going to be dy over dg times dg over dx, plus dy over dg2 plus dg2 over dx, plus dy over dgm times dgm over dx. Now what is this additional bit of logic actually buying you? Let's take a look at, is there something I can do here? No. There's another board. Okay. So for example, let me give you this function y equals some f of g of h comma x, sorry, h of x comma x comma h of x comma x. Now this looks really ugly, does it not? The function y, the value y is a function of x, but not just directly a function of x. It's a function of x. It's also a function of another function g, which is also a function of x, but also a function of h of x. And then y again is also a function of h of x, right? If I ask you to write the derivative of y with respect to x, did the audio just turn off? Can you hear me at the back? So let me see. Maybe this battery is kind of dying. I think you can hear me now, right? Okay. So now let's say if I want to compute the derivative of y with respect to x, this looks non-trivial, does it not? Because I have h, and then I have g, but g is a function of h is a function of x. The whole thing is really horrible. But let me draw the influence diagram over here. What are the things x modifies? I should use this guy. So just keep track of that equation. I can write this way, right? X, I have y, x directly affects y, right? And here you're going to see this nice distinction between a derivative and a partial derivative. What is the time? Am I running out of time? I'm seriously running out of time. But anyway, let's go through this anyhow, right? So x, but then what else does x affect? X affects h, right? So this is h. And f and h affects y. Correct? X also affects g, but then h affects g, and g affects y. Right? Now, if I draw this, it's very trivial for me to see exactly what the derivative of y with respect to x is going to be. Observe the difference between a full derivative and a partial derivative. Again, these are terms that you've encountered in your calculus, but this little diagram is going to explain it to you, right? This is going to be the partial derivative of y with respect to x, which is this guy, right? Plus the partial derivative of y with respect to g, which is this guy, right? Plus the partial derivative of y with respect to h, which is this guy. This you get? It was trivial. I just drew the diagram, right? But then, what is this complete or is something missing? What is missing? Partial derivative of g with respect to x and partial derivative of h with respect to x. Now is this complete? Why not? Wait, as far as y is concerned, this is complete, right? The rest are, so just look at what happens over here. Y depends on g, which depends on x. Y depends on h, which depends on x. That's about it. You don't have to worry about anything else. The question I really have to answer is, what is the partial derivative of g with respect to x? This term. And the diagram tells me everything. You can look at each node locally, right? What is the partial derivative of g with respect to x? Once again, I can look at this path. It's just recursion, right? And this path. That's going to be partial derivative of, this should have been full derivative, sorry, dg, dx, again, dh, dx. Again, you will observe the distinction between partials and full derivatives, right? So now the full derivative of g with respect to x is going to be the partial derivative of g with respect to x, which is this path, times the partial derivative of g with respect to h times the full derivative of h with respect to x, which is this guy, right? And then I can write the full derivative of h with respect to x. Guess what? It's already there, right? Just by drawing the diagram out, I can take a really complicated looking derivative and break it down and write everything out. Everybody with me? Right? And this you're going to run, and now this, I'm not doing this gratuitously. It turns out that you're going to be using exactly these formulae in your training, right? Remember this diagram. We're going to encounter it again. Questions? Anybody unclear about how I ended up with these derivatives? Yes?
I'm not sure why we try to expand such expression in the second line.
Which one? This guy? This one?
G, yes.
So this is a full derivative. So it's a partial of y with respect to g times how much does g change in response to x. But to know how g changes in response to x, which is the full derivative of g with respect to x, that's this guy, right? That has to consider how the various ways in which h influences g.
But the reason is because I see there's a link between the x and the g. Why we assume that we can't calculate the derivative of g over the derivative of x?
We already have. That's the second equation, right? So g is influenced by x in two ways. So all you're asking is, how is y, what is the influence of x on y through this path when you're looking at it from here? Which is the derivative of y with respect to g times the derivative of g with respect to x. This portion you're not really worrying about. And the derivative of g with respect to x, again, is fairly complicated, as the diagram will show you, but I can write it out. Make sense? The point is that at each node, you're just looking at the node. You're not looking at the entire diagram. That's the whole point of this. It breaks the whole decomposition down. It's a very complicated looking function. But then when I draw these influences down, I can look at each node. And at each node, it's going to be the partial along a path, which in turn is going to be the product of a partial and a full, right? That's about it. So it's a very trivial little decomposition. But immediately, the moment you begin drawing this diagram, all kinds of complicated derivatives become very simple. With me? Anybody else? Right, okay, yeah.
Not exactly sure about the difference between the partial g with respect to x and the complete derivative g with respect to
So this is over here. This is the over here. How does changing x change g out here? That is the complete derivative, okay. And this is, if I fix h, how does changing x change g? If I don't allow this link, how does changing x change g through h? Those are partials. Partials are where you fix everything else and modify one term. The full is where you actually consider everything. Make sense? Yeah. Okay. The distinction between partials and fulls should be clear. And the diagram should make sense, right? It's very pretty. Thinking of things in this way is really pretty and makes things so simple. Because you can take the most complicated functions and just simplify the whole thing. Anthony, question? No, okay. All right. So, and you can actually go through the basic definitions and show that this all works, okay? So now let's go back to this problem. How do I compute the derivative of the divergence with respect to a weight? I'm going to show a tiny 2-input network for illustration, where I have x1 and x2, I have a bunch of neurons, and then I have the output y. But then each neuron really is a 2-step process. In the first step, you compute an affine combination of the inputs to the neuron. In the second step, you apply an activation to this affine combination. So I'm going to separate these 2 steps out. I will show the plus, and then I will show the activation. This is going to be very important for the derivation of these formulae. So here we are. I've shown all the weights. I've shown all the activations. I've just shown a figure for the activation. But the key point is this y is differentiable with respect to this activation because it's differentiable, which means it's differentiable with respect to all these weights and the outputs of these guys. And pretty much the y is differentiable with respect to every single term in this network because it's a composition of differentiable functions, right? And once again, observe that this really is an influence diagram, right? This diagram is no different from the one that I just drew, which means that if I can compute derivatives over here, I can compute derivatives over here, right? But we'll see exactly how this happens, right? I'm including all of the various terms. I've expanded the figure out, and wait. I'm not going to derive this on the board because it will take too much time. But let's start with the scalar formulation. Here is the entire network. Is this the diagram? Yeah. Here's the entire diagram. Here is the entire diagram. This is the complete network. For notational convenience, we have an input. So here's how we've labeled everything. For each neuron, the affine combination of inputs is going to be labeled as Z. The output after an activation has been applied to this affine combination is going to be called a Y. So in the first layer, this is the 0th layer. The input layer I'm going to call the 0th layer. So Y superscript 0 is simply the input. Y superscript 1 is going to be the set of outputs of the first layer of the network. Y superscript 2 are the outputs of the second layer of the network, and so on. Y superscript n is the final output of the network. Z superscript 1 is going to be the affine combination of inputs to the first layer, and the activations are going to be applied to Z to compute Y. So also Z superscript 2 is the affine combination of Y1s. Right? Do you get the notation? So how do we actually perform the computation? If I give you an input, how do you perform the computation? How do you get the output? Consider this first unit. For this first unit, Z1, the subscript indicates that it's the first unit. And notice that this F underscore subscript 1 means that all of the neurons in the first layer use the same activation function. That's just my notation over here, my convention. So the Z is going to be just a weighted combination of all of the inputs. Again, I'm assuming that there's a fixed 1 over here, so I'm including the bias as a weight. Then at the next step, so this is just for the first guy, right? I can generalize this equation and say that Zj for any jth unit is simply going to be a weighted combination of the inputs. Yj, y, the set of y's, is simply going to be these activation functions applied to these z's. Then at the next layer, the z's at the next layer are simply going to be affine combinations of inputs, of outputs of the first layer. And then the corresponding outputs of the next layer are going to be the activation functions applied to z. I can keep doing this forward. Then again, you have the affine combinations of y2 and the activations applied. And this would go all the way down the network till you compute the output. Now, if I were to write a little pseudocode for this down, or the algorithm for this down, I'm going to initialize the y0 as the input. And then I just sort of scroll through the layers. In each layer, I first combine the affine combination of inputs and then apply the activation. So as you can see, just writing a little piece of code for the forward computation in a neural network, multi-layer perceptron, is literally just 4 lines of code at some level, right? So this is easy. If I were to write the forward pass down, this is the pseudocode for it. I'd go through all the layers sequentially, and for each of the neurons, I'm just going to compute the affine combination and then apply the activation. You'd never do it neuron by neuron. You'd actually do it as vectors. We'll see it later in class if I have the time. So now we know how to compute the outputs given the input. In the process, we would have computed all the intermediate values, all the z's for the hidden neurons, all the y's for the hidden neurons. So in other words, all of these colored boxes have been computed during the forward pass. These are things that we're going to have to remember when we want to compute the derivatives of the error with respect to the various parameters. Of course, first I need to compute the error itself. So I'll apply some divergence box outside here, which computes the divergence between my desired output and the actual output to give you the divergence. Again, this is all for a single instance. We are doing this for a single training instance. We are assuming that the divergence is differentiable. And then here's the process by which we are actually going to compute all of our derivatives backwards. First, we will compute the derivative of the divergence with respect to the output of the network. Then using the chain rule, we are going to use those derivatives to compute the derivatives with respect to the affine combinations that go into the output activations. Then using the chain rule, we are going to use these derivatives, the derivative of the divergence with respect to these guys, to compute the derivatives with respect to the weights in that layer. And then we're going to use the chain rule and take a step back and then compute the derivative of the divergence with respect to these guys. And then chain rule again, take another step back, you compute the derivative with respect to these z's. And then chain rule will give you the derivative of the divergence with respect to these weights. Then a step back, the derivative with respect to these z's. And you're going to take the step all the way backward, which is why we call this the backward pass. You're computing the derivatives from the output back all the way to the input. Questions? Let's go through the math. The math is very trivial. So long as you understand how this is being done, the math is very trivial. So first, here are all the parameters, right? First thing, I want to compute the derivative of the divergence with respect to each of these outputs. That is trivial. Depending on whatever your derivative function is, you can compute the derivative of the divergence with respect to the various outputs. We've already seen some examples of this, right? Now, so let's assume that I have the derivative of the divergence with respect to each of these y's. I've already computed it. Next step, I can compute the derivative of this divergence with respect to, say, this guy. That's going to be the derivative of the divergence with respect to this output, chain rule, times the derivative of this output with respect to this input, right? So this guy has already been computed. In the first step, we computed the derivatives at this position. The second term is simply the derivative of this activation function. So I take a step back, I'm going to get this, and again, the key piece is this: the derivative of this activation function is being computed around the current value of its input, which was computed during the forward pass. That's why we need to keep track of all of these terms in the forward pass, right? So here is the overall derivative. The derivative of the divergence with respect to this guy is simply going to be the derivative of the divergence with respect to the output of the net here times the derivative of this activation function computed at the current z value. So this is just for one of these guys, right? I can generalize this and say that the derivative of the divergence with respect to any of these guys is simply follows the chain rule all the way to that point. So nothing confusing so far, right? Now let's take a step back. Let me try to compute the derivative of the divergence with respect to, say, this weight. The derivative of this divergence with respect to this weight using the chain rule is the derivative of the divergence with respect to the z value over here times the derivative of the z value with respect to this weight. That's the equation over here, right? And this guy has already been computed because we've been walking backwards. What about the second term, the derivative of the z with respect to the weight? Now, you know that z equals weight times the previous y, right? So this z is going to be this output times this weight plus a bunch of other terms. So if I take the derivative of this z with respect to this weight, it's simply going to be this output. This is going to be y1 of n minus 1, which of course we computed in the forward pass. So you have the derivative of the divergence with respect to this weight computed using the chain rule in this manner, right? And I can generalize this for all of my weights. In general, for all of the weights in this layer, it's going to be exactly the same equation applied over and over again, right? So far we're good. What I have done is, so far I've come from here, computed derivatives with respect to this y, this z, and all of these weights. Let me take a step back now and compute the derivative of this divergence with respect to the output of this activation. Now look at this, how this guy affects the final divergence. This guy can modify this output, which modifies the final divergence. This guy can affect this output, which modifies the final divergence. Remember our influence diagrams? So now we have to sum over both of those. So which means that I'm going to be summing over all paths going out of this neuron. I'm going to compute the partial derivatives down that path, which is going to be the derivative of the divergence with respect to the z times the derivative of the z with respect to this y, plus the derivative of this divergence with respect to this z times the derivative of the z with respect to this y. And of course, these guys have already been computed when you were going backwards. And this term, again, if you look at this, the derivative of this z with respect to this y is just this weight, right? The derivative of this z with respect to this y is just this weight. So it turns out that this guy, this term, I can simply write the whole thing as these derivatives multiplied by these weights and added up. Questions, anyone? Right? You will have to go through the slides to get the notations and such like, right? But the concept is very clear, right? And then I can do this for every one of these guys. And then once I have done this, I can take a step back and compute the derivatives, use the chain rule to compute the derivatives at all of these locations, use the chain rule to compute the derivatives with respect to these weights, work my way backwards, all the way to the beginning, right? So here is the overall backward pass for computing the derivative of the error with respect to each of the parameters for a single input. First, you're going to compute the derivative of the divergence with respect to the output of the network. And then you're going to take a step back and compute the derivative of the divergence with respect to these guys. Then scroll your way backwards. First, you would compute the derivatives with respect to the y, then take a step back, compute the derivative with respect to the z, and in between, you're also going to compute the derivative with respect to these weights. And just, it's a very simple algorithmically, it's 3 steps within each for each layer. And so the overall pseudocode is going to look something like this. From the output layer, first, for the output layer, you would compute the partial derivatives of the divergence with respect to each of the outputs. And then you'd compute the partial derivatives of the divergence with respect to the affine combinations that go into the output layer. And then you'd work your way back down through the layers, and within each layer you're going to compute the derivative of the divergence with respect to the y, the compute derivative of the divergence with respect to the z, and somewhere along also the derivative of the divergence with respect to the weights. Right? I'm not going to go through these equations. One could do it. I will leave this as an exercise to you guys to actually go over the slides, and just to make sure that you've gone over the slides, I'm going to have these in the quiz. Okay. Now, something very interesting. The backward pass is extremely analogous to the forward pass. So here is the backward pass, going backwards, right? Here is the forward pass. What did I do in the forward pass? I was going forward, and in each loop I was computing an affine combination and then applying an activation to it. When I go in the backward pass, in each loop I'm computing an affine combination, but this time of the derivatives, and then doing the equivalent of applying an activation to it. So the forward code literally can be flipped, and you can use the same code for the backward pass, because the process is basically exactly the same. Questions? Right, there are some special cases. We've assumed so far that the computation of the output of one neuron does not directly affect the computation of other neurons in the same or previous layers, and that outputs of neurons only combine through weighted addition, that activations are differentiable. All of these things can be violated. So I haven't actually discussed these, but they are in the slides. So again, I expect this particular lecture is a toughie, so I expect everybody to go through the slides. And although I'm using the quiz as a motivation to go through the slides, there should be a different motivation, namely that there's information on the slides that is important to you. So the special case, vector activations where all outputs are functions of all inputs. So here, for example, if this y is a function of the entire vector of z's, I can write this vector of y's as a function of the vector of z's. And in this case, if you look at any particular y, I can actually draw these connections. The influence diagram is this y is influenced by all of these z's, right? Again, this z influences all of these y's. So if I want to compute the derivative of, I'll skip this bit a little, but say I want to compute the derivative of the divergence with respect to this particular z, I have to consider all the ways in which this particular z affects the divergence. So which means it's going to be the derivative of the divergence with respect to this y plus this partial derivative times the derivative of the divergence with respect to this y plus times this derivative plus the derivative of the divergence with respect to this y times this derivative, and so on. You're going to have to sum over all of them, which gives you these nice vector equations, right? So, questions? I'm skipping over a bunch of things because the really interesting stuff is the vector formulation. We've seen how the whole thing can actually be done when you look at all of the neurons one at a time. But it's much more convenient to think of the entire thing as one vector process, simply because the arithmetic is simpler. You can use matrix libraries which make operations much faster, and you can restate the entire process in vector terms. So in fact, in any real system, this is what you're going to use. In fact, if you're writing code, this is what you're going to use. So let's see how I do this. First, I can write all of these weights as a matrix. I can write all of these x's as a single, all of these guys as a single vector. I can write my biases as a single vector. I can write all of these z's as a single vector. I can write all of these y's as a single vector, right? And then when I do so, here is the little equation you're going to get. You're going to get that zk at any layer is going to be the weights matrix times the y at the previous layer plus the bias. and the y is simply the activation function, which you can think of as a vector activation applied to this affine combination. So here's how if I think of the entire thing in vector terms, here's how the operations are going to look. I'm going to have y0 is initialized as the input, and the affine combination at the first layer is going to be just the weights matrix times y0 plus b1. And then I have the output, which is simply the activation function applied to the affine combination. And then again, I multiply that vector by the weights matrix and add the bias, and then apply that, then compute the activation, and I can do this all the way forwards. So when I actually think of the whole thing, one thing to note is that this actually sort of explicitly shows you that a neural network is just a huge nested function. But then more importantly, if you just if I think of it algorithmically, here is the really trivial forward pass for when I think of the whole network in vector terms. I initialize my y0, then for each layer, first I compute the affine combination of the outputs of the previous layer, and then apply an activation to it. And the final output is simply going to be the output of the final layer of the network. So in vector terms, the entire forward pass is this really trivial piece of equation that you can, if you were writing code for it, this is all the code is going to be, right? What about the backward pass? For the backward pass, again, first you have to sort of think of, now you have to worry about the calculus. How do you actually perform the calculus in terms of vectors? So this network is a nested function. The output is this activation applied to the output here, which is simply this activation applied to an affine combination of the output here, and so on. So it's the whole thing is a nested function. The divergence over here is a nested function of all of these parameters. Doesn't really, and then I can use simple chain, the simple chain rule that we use for nested functions. So first, we define a Jacobian. If I have a vector output of a vector input, the Jacobian matrix is a matrix of partial derivatives. It's going to be, each row in the matrix is going to be the derivative of this guy with respect to all of the inputs. So the first row, for instance, is the derivative of y1 with respect to z1, the derivative of y1 with respect to z2, all the way to the derivative of y1 with respect to zd, right? And each of the rows is going to be a row of partial derivatives of one output with respect to all of the inputs, okay? Now, if I use vector notation, I have y equals f of z, right? And you can easily check that delta y equals this Jacobian times delta of z. So once again, it satisfies our definition of a derivative. Our definition of a derivative is the term that multiplies a small change in delta of z to give you a delta of y. So this, again, we're going to keep coming back to this definition of a derivative because it's really important. This guy is satisfied, right? So if my activations are scalar activations, you'll find that the Jacobian is simply a diagonal matrix. If my vector activation is vector where these diagonal terms are just the derivatives of these individual activations. If my activation is a vector activation, this Jacobian is going to be a full matrix with lots of partials. Again, look at the slides, right? So now look at a very special case, affine functions. If z equals wy plus b, the derivative of the Jacobian of z with respect to y is simply going to be this matrix w. Right? This is just, you might almost think of it in terms of scalar terms. And the Jacobian of z with respect to b is going to be an identity, right? So now let's look at the chain rule. If I write y equals f of g of x, again, this is exactly the same chain rule that we use for scalars. The one important thing is the order in which the multiplications happen. I can write z equals g of x, y equals f of z, right? So using our notation, delta y equals the Jacobian of y with respect to z times delta z. Delta z is the Jacobian of z with respect to x times delta x. Plugging the two in, the Jacobian of y with respect to x is going to be the Jacobian of y with respect to z times the Jacobian of z with respect to x. Now these are matrices, So the order in which the multiplication happens is important. You can't flip the order. You can actually check that all of the dimensions fit, but this is clear, right? Now, suppose y is not a vector. Suppose y is a scalar, like the case of the divergence. The same rule applies. So this is going to be the derivative of the divergence of d with respect to z times the Jacobian of z with respect to x. Again, I'm using the same note the chain rule, right? And one last thing that you want to actually check is, suppose I have something of this kind, which is a scalar, which is some function of w times y. Then the one special rule that you're going to get is the derivative of this divergence with respect to w is going to be y times the derivative of d with respect to this guy, z. So if you check this out, this is going to be a matrix of the appropriate order. So this is the one key piece. So suppose I have a vector here, multiplies a matrix W to give me B, right? Then the derivative, and this goes into a scalar D, divergence. Then the derivative of divergence with respect to W is going to be the derivative of the divergence with respect to B, which is going to be a vector, times the derivative of times E. Or is it it's the other way around? Yeah. What have I got here? Let's see. This guy. Well, I won't confuse myself too much because we're running out of time, right? But the whole point is, again, please take a look. So here's how this whole thing helps us, right? I can start off by computing this first derivative, which is a vector. Then at each point, I just keep, as I go backwards, what you will observe is that I'm just going to keep multiplying terms to the right-hand side of my of the current partial derivatives. So I should probably spend a few minutes going through this in the next class. But then the first step, you compute the derivative of the divergence with respect to y, which is going to be a row vector. Then over here, this derivative is going to be computed by multiplying the derivative with respect to y with this Jacobian. Then this guy is going to be computed by multiplying the derivative over here by the subsequent derivative, which is going to be the weights matrix, this guy, and you keep working your way backwards. I'll cover this in the next class. I'll stop right here before I confuse you too much. Okay?